So today I would like also to talk about hidden Markov models, and basically I'd like to kind of motivate them in a way where so hidden Markov models are in contrast to like the other kind of approaches that we have looked at, not just classifying a single observation at a time, but they kind of take into account the dynamics of sequences. So for example, you can have like a time series of any sort, maybe one of the most common time series that you can imagine is the speech, continuous speech that could you could try to classify speech into like you can recognize words that I say, you can recognize the topic I'm talking about, and there are various ways to kind of do this. So for example, if I want to recognize a word, or I would try to identify a sequence of phonemes, so like to say what, that like I would need to identify those three phonemes after each other. To recognize a sentence, I would have to like recognize words after words, and so so this is kind of like what hidden Markov models are really good for and are excelling at. Like hidden Markov models, it took a very long time for deep learning to beat hidden Markov models in speech recognition, and so they're really like very good classifiers for speech or like for sequences in general. And so in Markov models are kind of special in a sense that we assume that there is a series of like states that I go through in order to generate a certain sequence of observations. However, these these sequences through the states are unknown to me. Like I do not see what state like the hidden Markov model is in at any given time. I have to estimate that. I cannot observe those values. That makes it a hidden Markov model, obviously. And the only thing that I observe are the expressions of the states and their transitions between separate different states. So in a hidden Markov model, and so one of the things that's important is like we do not kind of learn the structure of the hidden Markov model. I basically predefine it. I say like, okay, to recognize phonemes, I want to have a three-state hidden Markov model. Why would I do three states? Well, in phonemes, so this for example could be a phoneme right here. Well, you have an onset, you have a sustain of a vowel, and then you have an offset. Okay, and that kind of like can be motivated. You can motivate your structure of the hidden Markov model through kind of like a top-down information that you have about the series of sequences that you have. In DNA, for example, you would have the knowledge, okay, I know that there is like a little bit of an expression in the genes that starts off a sequence, then you have the kind of like the gene, and then you have an end of the gene sequence. I'm not a biologist or a chemist, so I don't really know if that is completely true, but you would have these kind of state transitions, and you could try to model like a DNA sequence through this kind of top-down information if you have that, okay? So this is kind of like what we're doing, and for phonemes, you would have these three states, and you make observations, and you try to identify, or like you try to guess what state sequence happened in the hidden Markov model, and you try to estimate the likelihood of your hidden Markov model that is representative of a certain phoneme, like what the likelihood is that this hidden Markov model has generated this sequence, okay? And and then, so if you have 40 phonemes or 42 phonemes, you would have 42 of these hidden Markov models, and each of them is trained on a different phoneme only. You only use positive examples to train a hidden Markov model, okay? You don't use negative examples really. So you would train each phoneme on your, each hidden Markov model for the phonemes separately, and then you would get a new sequence that these models have never seen before, and you simulate through those models, and at the end you look like which one has the highest likelihood of having produced this sequence, right? And then you pick that one. That's kind of like how classification in hidden Markov models work. So you pick the one that has the highest likelihood of having produced this observation sequence. But you never really know like which states it was in, like, because it's not observable for us. And so that's how you get a phoneme. Then obviously what you would try to do is like, you have now your assumptions. Okay, these are the phonemes that I observe in sequence, and then you could put that into like your word classifiers, and you would then try to, okay, so the sequence of these 3 phonemes makes the word what, of these 5 phonemes makes a different word, and so on. So that kind of like kind of allows you to generate word classifications. Okay, so that's like just kind of like a basic overview of what hidden Markov models are used for and what they're good for, and we're going to go into detail with that. But before we do that, I would like to first discuss like what Markov processes are. And so Markov processes, and they're like, because hidden Markov models, like if you do not restrict your sequence classification or sequence generation variables enough, you run into severe computational issues. Like you cannot just compute the likelihood for an unconstrained time series. So what we do, we constrain our time series a lot. So for example, if you do not constrain your time series of what you're going to say, you have to, for example, and so in this case, Qt is basically a state at time t, and if Qt is equal to Si, then we are in Si at time t, okay? So, and the Si's are these states that we have. And so, like to know, or to get the probability of in the next time step being Sj, we would have to look at all the states that we were before to make that prediction proper, right? However, in Markov processes, we don't make it so hard for us. Okay, so what we do is basically we cut off that tail until here and just say the next step is only dependent on the previous step. Okay, and that's the first order Markov model. And second order Markov model is the next step is only dependent on the previous step or the time step that I'm in right now and the one that I was in before, but only 2 of those. And so that makes it a lot easier for us, and we can reduce this whole thing here to just this probability. Okay, so that's very important. So like in first order Markov processes, we only regard the previous time step or the current state that we're in right now as important for measuring where we're going next. Okay, so basically you can say that given the present state, the future is independent from the past. Okay, so today is the last day of the rest of your life. Do you have any examples? First order Markov processes. I always give the same example. Some people have seen this before, I think. But so politics, is that first order Markov process? Unlikely. Current times, it's a random process, independent of everything. But one very famous example of like what a Markov process is like a lot. I love chess, like riddles, or like try to solve chess puzzles, and you never need to know how they arrived at the chess puzzle state right now. you can always solve it from right here. You don't need to know what happened before. And so chess clearly is a Markov process where you have the observation, and everything that you do from now on is just dependent on what you see right now. Even if the person has like a strategy behind, etc. But that doesn't really matter because you can infer the strategy from the state as it is right now. Okay, so that should be kind of clear. Do you know any second order Markov processes? I don't know an example really, but it could be like a special form of chess where you have the last two, like you move twice or something like that. I don't know. Okay, so that's that should be clear. Okay, so one important thing is that it's not just well, okay, so we kind of further simplify our problem a little bit in a way that if you have this model which has like a certain number of states, and chess is not a great example because it can have like a lot of different states, and Go is even worse. You can have even more different states at any given time. But in discrete or in discrete Markov processes, and the Markov process that we want to think about, we have a few states, maybe like 3 or 4 states, and it is important that we also want to consider, like we consider this transition from state I to state Sj as kind of like a constant. So this probability to move from one state to the other doesn't change over time. Okay, so it's fixed. Like we have a model that's fixed, doesn't change. Okay, we don't kind of want to like deal with changing probabilities between states. And so if we do this, well, now we can actually represent a hidden Markov model through a matrix of state probabilities. Not a hidden Markov model, a discrete Markov process through a matrix of probabilities to transition, right? So I can have a 3x3 matrix, and I have like 3 states, and I have in each of these items, like I have 9 different probabilities to move from one state to the other. And obviously, like if I stay on the diagonal, I am in one state and I go to the same state again, right? So we can come up with a matrix, and each row sums up to 1 because there needs to be like the probability should be 1 to move from one state to the next, because we always move like in a discrete time step. There's a little bit of an addition to this where we need to also start to jump into the the Markov process or the Markov model, and so we need to have like a couple of start probabilities to come from kind of like somewhere out here into the model, and that is represented with 3 more variables or probabilities, which is basically the starting probabilities pi I, which also sum up to 1. So to get into the model, you need to have like a probability of 1 to actually start the process. Okay, and so if we think about this kind of like model now, we can now actually represent a lot of the stuff that we talked about previously with the graphical models through like a Markov process, and you can think about this kind of like a state transition matrix. So if I'm in sunny, well, in the next second it's going to be sunny again, hopefully. So the probability is kind of high, but at some point it might turn cloudy or it might turn rainy. Okay, so you have different kind of probabilities here, and let's do some examples of observable Markov models where we actually see each state. So in like sunny, cloudy, rainy, etc., we can observe the weather. We see what's happening, so we don't have to worry about these hidden states. So all of our observations are kind of obvious to us, and we know at each time t, in what state qt we are. And if we now have this matrix, the A matrix, where we have all the transitions, probabilities, and we have the starting probabilities, the pi vector, then we can compute any, like the likelihood for any sequence that we want, okay? And it's very simple by just basically like computing this. So if we have, if we want to compute the probability of a certain state sequence or observation sequence, given our transition matrix and our starting probabilities, we can just compute this probability as such. And I have an example. So what if we start off with, we have like a number of urns. In this case, we're going to have 3 urns. Each of those urns has like one type of balls in it, and they are right here, urn 1, 2, and 3. This one has only red balls, this one has only blue balls, and this one has only green balls. You can see it, they're see-through urns. And then you have me up here, and I'll start just picking different balls, okay? And we have these different states that we can observe. So whenever I pull one, we observe a state, okay? And my starting probability to start off with state red is half, and the other one is like split up like that. And then the transitions for me to go from when I pull the red to the next red, or to the next blue, or to the next red, to the next green, is defined by this matrix. So for example, if I pick the red first, I have a 40% chance that I'm going to pick a red again, but a 60% chance to pick one other. But if I'm like, for example, in the green already, a very unlikely switch over. Okay, so I can express these kind of probabilities. And with these 2 variables, I can generate any random sequence. Okay, so let's try this out. Basically, this is my observation now. S1, S1, S3, S3. So what do we do? So first, we start in S1. What do we do?
You picked red?
I picked red, yeah. So we have these 2 variables.
So that's an entry variable.
That's an entry.
So it's 0.5.
0.5
times.
We stay in S1.
0.4.
Yeah. And we go to S3.
S3 is from 0.3.
Yeah. And then we stay in S3, 0.8, right?
0.8.
And then that's how you do that. So this sequence has the probability of 0.048. That's kind of how you would do that. Okay, so if you have this model, you can compute any of these sequences and the likelihood of these sequences. But now the kind of like the question, however, though, you could ask yourself is like, so how do we know that this is the model, right? Well, how do we learn these parameters? How do we learn the pi and the transition probabilities? Training data. So we need sequences to observe, right? So given a number of sequences, we can compute these variables. And so we would do this, for example, for the starting probabilities. What would we do? So we have 10 starting sequences, or it's 10 sequences. And how do I calculate the...
So red's over 10, and then yellow's over 10, or...
Exactly, so it's basically you count how many times you start in that state versus like how many sequences in total you have. And then for where QTK is the state of in the time sequence. And so T in this case is 1, so that's the starting times. Okay, so how do I get now to the transition probabilities? From like moving from state I to state J.
You need to denominate and say, this is how many times I moved from I to J, and then this is how many times I moved.
From
Over
I to anywhere.
to anywhere.
Right, yeah. It's because we want to normalize it over one row, somewhere to one, so we don't have like every transition ever, but only the transitions from I. So this is the likelihood from like the number of times I go from I to j over all the times I end up in I and go somewhere else, or go somewhere. Okay, cool. So this is how you do that for observable Markov models. Now, for hidden Markov models, that obviously becomes a little bit more difficult. And so we require to kind of like define a couple of different things here now. So in hidden Markov models, the states are not observable. So I do not know in what state I am. However, when a state is visited, an observation is produced, right? So like we see something happened, okay? So in the urn example, that will mean the following. There's a curtain here, you don't see the urns. However, I am still here, and what I would do is I would go somewhere here, pick up a ball, and then show it on the side for the curtain, and then put it back. Why do I put it back? Just a quick intermission question.
To keep the overall probability of draw sort of change or run unchanged, right?
Yeah.
Because you don't wanna run out of.
Because yeah, if I don't put it back, I change the probability of pulling that type of ball from that urn and so on. So like we want to keep that constant, so we put them back. Okay, and that in the previous example, I also put the ball back. Okay, because otherwise I would change the probability transition and to draw these balls anymore. Okay, so that's important. So we see these observations new, and now we also define kind of like the emission probability, Bj of m, which is basically the probability when I am or if I move into Sj to observe the discrete observations. So here we have like a discrete set of observations that could be like red to green and blue in this state, okay? And so we're going to get to the example of the urns again in a second, but there's one big change now. So in the observable Markov model, we knew that there are only red balls here and only green balls here and blue balls there, right? But in the hidden Markov model, there can be red and green and blue balls in each of the urns, okay? So that's very important. So you can observe any of those colors when I pull them from a state, okay? But each state has a different probability to produce those, okay? So this state might have a higher probability to produce green ones and a lower probability to produce red ones, but each of them can still produce all of them or make those observations. Okay, right, and again we assume a homogeneous model that does not depend on t, so we put the balls back, okay? So now what we can get is observation sequences. So we can make observations and then we have these sequences, like red, green, blue, whatever. But we do not know in what state these things were pulled from. But we want to infer the state sequence. That might be an important task for us. And we'll get to the main task for hidden Markov models in a second, but this could be a good task. And typically, it is possible that many different sequences produced this observation sequence. So, but we want to find one of them, right? And we want to find the one that is the most likely, okay? And each of those sequences has different probabilities. Yeah, and we are interested in the one sequence that obviously made it was the most likely one, okay? All right. So if we go back to the urn example, and now each urn holds different colors, as I said, and we have a probability that a ball of a certain color is drawn from J, from urn J, which we denote with this Bj of m, and we observe a sequence of balls that are pulled from the things, and like I show them from on the side of the curtain. and we're putting them back in, and in this case now we observe the following sequence, which is red, red, green, blue, yellow. Okay? So, and we also have a fourth color now. So we have four colors, but whatever. So we're not restricted by the number of colors anymore, but we still have like 3 states or something. So how do we basically now, if we know the probability that a ball is chosen from a certain urn, or a certain color is chosen from a certain urn at each time step. So what if we know that probability? What do we have to do to basically compute which sequence of like 3 urns has produced this?
We would need to make all the combinations seeing red coming from the first urn, red coming from the second, red coming from the third. So these are the probabilities. And then the second red coming from the first, and second red coming from the second, and all of these.
Exactly. So we would have to have like a combinatorically exploding number of possible ways to calculate this, right?
Yeah.
So and this is exactly what this kind of represents, because we can start off in here, we can start off here, we can start off in here, and then we observe these things, the different colors, but then I can go from here to here with this probability, but I can also go from here, and I could go into any position, right? And then I can go from here to any position as well, and so on. And so the complexity of this is dependent on the number of states and the number of observations I make in one sequence, right? So that can become really, really difficult to do. And but you'll
also presetting all the probabilities means that you would somehow have to test with what probability the first urn gives you red.
Yeah. But in this case, we assume we know all the variables we know them, but it's still really hard.
But in real life, you will have to calculate it.
You will have to train it, yeah. So we're gonna get to and that is done as we have discussed before in one of our lectures. So to basically learn responsibilities of certain like states or models, or mixed, in that case it was mixture models, for a certain data point that doesn't have a label, we use the expectation maximization algorithm, and it's what we're gonna do again to learn these variables. Okay, the pi's and the alpha, the a values. But basically, what you can already see in a sense is if I'm only interested in the most likely sequence, right? I only have to compute a couple of things, right? Like I just need to know at each time step what is the most likely point to be in, right? And this is kind of like where the Viterbi algorithm kind of comes in and helps us reduce the complexity of this calculation. And we're going to get there hopefully soon. All right, so a couple of definitions that we need, and if you want, you can call a hidden Markov model a 5-tuple of the following things. States, we have n different types of states. In our hidden Markov model we have observations, V or O or whatever. We have transition probabilities from each state to the other. We have omission or observation probabilities for each state to produce a certain observation. And we have initial starting probabilities. So we add these guys here, the omission probabilities now, okay? So in Markov models so if we have all these 5 tuples, so the states, the observations that we can make, transitions, the observation probabilities, and the initial start probabilities, but we can produce sequences. That's kind of cool, right? So hidden Markov models are generative models, and they can produce sequences. But as usual, we're not interested in generating sequences mostly, but we're interested in like having a sequence, trying to detect or classify like which model has produced this sequence. Okay, and so we talked about this a little bit, but we can use hidden Markov models to predict or to do speech recognition, and you can have like, for example, like this 3-state model where you have a beginning, a middle, and an end state to calculate or to calculate the probabilities of observing a certain phoneme, and you would have like the number of phonemes you have, that many models you have there, and you would basically compute the probability for each of the models to have produced this sequence, and then you decide the one that is most likely, and you choose that one as the class that has won the competition, and you would then try to go from phoneme levels to word levels, and then from word levels to sentence levels. Okay, these are all possible hidden Markov models. Yeah, so this just for classification. We classify using hidden Markov models, we have, for example, a hidden Markov model per class, and we choose the one that has the highest probability to have generated that sequence. Okay, so that's basically how we use hidden Markov models for classification. That's just basically like what we're doing here. So again, we're not trying to find a separation hyperplane or anything with these. We're basically looking at the likelihoods that a certain model has produced a sequence, and choose the one that has produced it with the highest likelihood. That's the model that we're going to say, that's the class that this observation belongs to. Okay? All right. So let's talk about the 3 main or basic problems that hidden Markov models have. And so the first problem that we want to solve is, given a certain model, we would like to evaluate the probability of any observation sequence, namely P of O given the model lambda. And so why do we need that? Well, to do the classification, we need to calculate this, right? We need to know what the probability of a given hidden Markov model is to have produced a sequence. Okay, that should be fairly clear why this one is important. The second one is, given a certain model and an observation sequence, we would like to find out the state sequence which has the highest probability of generating this one. Okay, namely, we want to find Q star that maximizes this probability. Okay, that one's not so clear why we need this, but it will become clear in a moment. Okay. Well, if you actually care about the state sequence, it might be important. Like for classification, we wouldn't need this information. Like, it's not that important.
But that's a diagnosis, right? That's just how you set the diagnosis and know.
Right. But you also need for a couple of other things. And then the third problem is, well, how do I train them, right? So how do I find the model lambda star here that basically has the highest likelihood, or like, so given a set of observations, we like to maximize the probability that a model fits that or generates this set of observations, okay? So that's training hidden Markov model, okay? Let's go through like each of them separately and start off with the first one, which we call, the evaluation problem. So, given an observation sequence and a state sequence, the probability of observing O is this, right? That's pretty simple. However, as we know, we don't know Q. So we don't know what these states are, okay? So we need to do something else. The something else now is, well, let's just compute the probabilities of any state sequence to go from one state to the other. And that is only dependent on the transition probabilities and the starting probabilities, right? So I don't need my observations here, so I can compute this by this, right? But there are many, many, many different state sequences that I can have. And then the biggest problem now becomes that the joint probability, or like the problem now is, well, if we can compute all the likely state sequences, which are many, and we have an observation sequence, well, I can compute it as such, where I have now the Q's, the B's, the transitions, and then again like B, A, B, A. So we have observations in there as well. So that becomes quite a computation for one observation sequence and one state sequence. But now the problem is to get from this to, well, to the P of O given lambda. We now have to compute the margin over all possible Q's. Okay, so that basically is this. This is the evaluation problem that we have, and now we can compute this, right? but to be able to compute this this here, we need to marginalize over Q, and that is crazy. Like that, it's really impractical, and it's like O of n to the power of t. So that's a lot. But fortunately, there's a way to efficiently compute this, and this evaluation algorithm is called the forward-backward procedure, and basically the number one idea here is, like, first of all, we do something recursively. We do it step by step by step, but we also split up our sequence into two parts. So we observe time t right now, and we split it up in the likelihood of arriving from the start in this point, and the likelihood of arriving from the end in this point. So we split it up into two parts, okay, to end up in this. And so first we look at the forward procedure, and then we look at the backward procedure. Alright, so the forward procedure looks the following way. So basically we define a variable, alpha ti, which is the probability of having observed a t many observations and being in state Si, given a certain model. Okay, and so for alpha I, alpha 1, that we start off our recursion, we can compute it as such, where basically we start off with a point. So we have the starting probabilities to start off in state I, and observing observation 1 in that state. Okay, and remember, we have all the pi's, and we have all the b's, and we have all the a's, because we have the fixed model, right? And then for alpha t plus 1, so like our recursion step, this is our initialization, we now compute it as such. So first of all, we have the observation sequence until t plus 1 now, going to Sj, and this can be split up into the probability of observing observation t plus 1 in Sj, times the sum of coming from any other state into that position here. And so we have to sum up, so we can come into this state from here, right? So we have to sum up over all of them to get in there. Yeah.
Shouldn't that be the maximum instead of the summation?
No, because we, in this case, we only compute the probability of ending up in that point. Not like we're not just interested in the most likely path.
Oh, okay.
Yeah. So we're interested in like ending up in this location, but through all paths. Okay. And then now this can, however, now be described as following, because this is our b, j of ot plus 1, and this part here is the sum over all the alphas that we defined before times the transition. Okay, so that like basically reduces this computation problem into so if we have the alphas from the previous states, we just have to remember those and not have to like recompute those. Okay. So in other words, alpha explains that the first t observation ends in state Si, and we basically multiply the alpha with the probability to move from Si to Sj. And as there are n many possible previous states Si, we sum over all of them. Okay? And bj ot plus 1 then is the probability that we generate the t plus first observation while being in Sj. So that's kind of like what this tells us. And for us to know the probability of having produced this observation sequence by the model, so that's our evaluation problem, we just have to sum up over all the alphas. Okay? And again, to have a model observe a sequence, we don't just need the most probable path, but we can go every path that's possible to compute basically the likelihood of having observed this sequence given a certain model. So every possible path, even if it's like a very improbable path, counts into that calculation. Does that make sense? Okay, and so basically, if you think about this here, what you want to do is you want to walk all the paths and end up here and basically sum up over these points, like what the probabilities are to get at that P of O given a certain model. And the cool thing is that basically if we have computed the forward to this one, we don't have to like calculate any other probabilities anymore. So once we have these values here, we can just go on to the next, and so we reduce our complexity a lot. We don't have to like go through all the possible iterations with this approach. So this basically brings down. So alpha t, capital T is the probability of generating a full observation sequence and ending up in Si. We just sum up over all possible end states to receive P of O given lambda, and computing this is O of n squared times length of the observation sequence. So this solves our evaluation problem, but we will also need the backward variable where we go from the end into like a previous time step, and we will need that later, so let's just define it here. So basically what this probability beta now is basically observing the tail end of the observation sequence and being in Si at time t, okay? And this can now also be computed recursively, and in this case we start off with capital T being 1, so like at the end we start off with 1. If we started off with 0, well, obviously this computation would be meaningless. But so we say every state has an equal likelihood of being at the end, and then we need to have our recursion steps. Basically, now these are the previous observations, so the tail end, and then now being in state Si, that can be split up the following way, where You just have to trust me on this one here. But in the end, you can reduce it to Aij, so which is the transition probability to go from I to j, and to observe observation t plus 1 in state j, and having the other part, the further part, times the further part. So beta explains everything from this side, and then we calculate the observation probability, like that's bj of t plus 1, and then we can come from any of these states into here, okay? That's why we need to sum here and transition over that one. Okay? Alright, so basically, in other words, when in state Si, we can go to n possible next states. Oh yeah, sorry, it was not the sum over like these. It's the sum over going into any of these states. Sorry. And then while in state as j, we generate the t plus first observation, which is the b of t plus 1, and then multiply that with the rest that we have already calculated. So that's our backward variable. Okay. And we are going to use this backward variable now, so the beta, for our finding the best state sequence, and that's where we will use the maximum in this case. So we want to, this is a second problem. Here we have an observation sequence again, and we would like to know which one is the most likely state sequence, Q, for this problem. And for this problem, we actually now define a gamma probability, which is basically the probability to be in state Si at time t, given an observation sequence and a model. Okay, so the gamma is now dependent on the entire state sequence, and you can already guess what kind of like is going to happen. So the gamma is going to be split into two parts. The one part is going to be explained by the beta. The other part is going to be explained by the alpha, and we're going to have just in the middle the observation probability of this time step t now. Okay, and so basically you have so this is the probability of being state I given an entire observation and the model, and in the end basically it splits up into like everything that happens until t, which is our alpha variable, and everything that happened from t plus 1 on, which is our beta variable. And then this is basically split up into alpha and beta, and then we normalize it so that we make sure that we don't have any funky variables for these gamma values. Okay, and so we normalize it over all the possible states at time t. Okay, and so this is basically explaining how we can and this gamma variable is going to be important, but it basically splits up into this forward and backward variable, and then we and the numerator explains the whole sequence, and the denominator normalizes the term to guarantee that gamma over all possible states I at a given time are 1. Okay, so to find the most probable state sequence now, we select the maximum at each time step t. Okay, so basically Q star of t is the argmax of which states are possible at each time step, and t is basically just iterated from 1 to capital T. And if we remember that correctly, what states we chose, which i's we chose at each time step, we then have the most probable state sequence. The only problem though is that this simple algorithm doesn't really work with like weird transitions from like Si to Sj, where there could be, for example, no connection, and so the Viterbi algorithm helps us to compensate for these kind of issues. And I'd like to talk a little bit about the Uterby algorithm now. Basically, again, so given a state sequence and an observation sequence, we define this delta t, which is the probability for the path with the highest probability that accounts for the sequence until time t and ends in Si. So this is the maximum of the state sequences and the observations. And again, we use recursion to compute delta t plus 1. The optimal path can be read out after the fact through like back propagation. And the initialization for delta I or delta 1 is basically the same as we had for the alpha value before. And then this is kind of our backtracking variable that we're going to keep track of. And then for our recursion, now we have the delta t minus 1, alpha aij bj observation t, and here we just take the most likely one, and for determination we just p star is our most likely state transition probability, and this is the most likely end state, or state at time t. And then for backtracking, we just like go through all the states that we had. All right. Other questions? So it's like just kind of like a basic overview of like how we solve these problems of like knowing if the model, like what's the probability of the model to produce a certain sequence and what's the most likely sequence through quadratic programming.
Are both of the algorithms guaranteed to find the best sequence? Is there any chance that
so this algorithm, yeah.
One sequence
So you can imagine that there is a little bit of an issue. If you have, for example, at any of these time points, the exact same probability to go from one or the other, then you have a problem, right? So it's not guaranteed that like if you have these issue like this issue of like having the same probability, but that's very, very unlikely to happen. But if it does, I mean, like, then you would want a quantum computer, I guess. So that you can move all the paths at the same time. So yeah, and all of this would not be a problem with quantum computer. You need Uterby algorithms, which is computed at once. So we should work on that. So yeah, so next week we're gonna finish up on this, and on Wednesday I think I'll do a little bit about like classifier fusion, and then we're gonna do deep learning. Cool.